Hello everyone, I'm Hyungsub Kim. I'm a PhD student at Purdue University. Today, I would like to talk about our new patch verification framework. Its name is PatchVerif. This work has been done with my collaborator, Ozmen, and my advisors, Berkay, Celik, Antonio Bianchi, and Dongyan. Let me first explain what robotic vehicles are. If a vehicle autonomously operates by itself, we can call such a vehicle as a robotic vehicle. Nowadays, the use of robotic vehicle is dramatically increasing. You can find such robotic vehicle in everywhere, such as submarine under the water, drone in the air, and a robot on the ground. Okay, then let me explain what faulty patches are. If a patch code snippet created by the developers breaks on existing functionality of the software, we can call such a buggy patch as faulty patch. So there are three different types of faulty patches. First, the faulty patch only partially fixes a buggy behavior, which means that we can still trigger the buggy behavior in different program contexts. Second, the faulty patch fixes an incorrect behavior, but breaks another correct behavior. Third, the faulty patch adds a new functionality of the software. However, unfortunately, the patch code includes a buggy code line. Okay, then why faulty patches important in robotic vehicles? There are two reasons why. First, the creating correct patches for RV control software is error-prone. In fact, while we are doing the previous research, we discovered that developers create more than 300 faulty patches in past 5 years, which means that faulty patch is a common issue. Second, faulty patch cause unwanted physical behavior such as mission failure and unstable position control and even physically crash on the ground. Okay, then why is creating patches for RV control software challenging? The main reason is that understanding patch-introduced behavioral modification is hard. In order to clearly understand this challenge, let me explain a motivating example. To understand this example, you first know what is pivoton. When this vehicle on the ground near from a corner, this vehicle started to decrease its ground speed and turn toward a next waypoint. So this is same as our real life. When you drive your vehicle on the physical road and then you need to make a sharp turn, you must decrease your vehicle's ground speed. By doing this vehicle can prevent rollover accident at the corner. However, unfortunately, the developers create a faulty patch related to this pivoton. Developers remove a code line in red color and add a new code line in blue color. The removed code line in red color returns dynamically adjusts ground speed according to the vehicle's current location. On the other hand, the new added code line in blue color always return a constant ground speed regardless of the vehicle's current location. As a result, after we deploy this faulty patch, this vehicle failed to decrease its ground speed at the corner. As a result, this vehicle started to deviate from the planned navigation path. Unfortunately, this is dangerous physical behavior because this vehicle can be rolled over due to the high speed at the corner. The one interesting fact is that developers noticed this buggy behavior after 3 months of deploying this faulty patch. What is the meaning of that? Which means that the test cases created by the developers failed to trigger this buggy behavior, also failed to detect this faulty patch. Then why do test cases created by developers fail to detect this buggy behavior created by this faulty patch? The main reason is that triggering this buggy behavior requires two specific physical conditions. First, we need to create a sharp corner by using waypoint. Unfortunately, the the manually created test cases do not exercise such a sharp corner. Second, we need to set a high ground speed such as 10 meters per second. Also, unfortunately, the test cases created by the developers, they do not exercise such a high ground speed. That's why the test cases was not enough to trigger this buggy behavior. Okay, the main limitation of the manually defined test case is that they always test the same scenario again, regardless of the patch code. In order to tackle this issue, our main idea is that, okay, then we can mutate test cases based on a given patch code snippet. That's why we developed a new patch verification framework. Its name is PatchVerif. PatchVerif consists of 5 different components. Let me explain each component step by step. In the first component, we aim to understand a given patch code. In particular, we want to understand how the patch code changes the physical behavior of the RVs. Also, we aim to infer which specific environment condition can affect the patch code. Okay, but how can you achieve these goals? In order to achieve these goals, we conduct a static analysis. First, we extract all name of variables and functions in the patch code. Next, we filter out all but nouns from the variable and functions name. This step is for removing the special characters such as ampersand. Next, we match the extracted term on the left side with a list of physical state and environment condition in the synonym table on the right side. We manually create this synonym table. The first column consists of a list of physical state and environment condition, and other column consists of a list of synonyms. For example, in the case of get ALT frame, we can match this term with altitude physical state. Why? This is because ALT is one of the synonyms of this altitude physical state. By doing this, we can notice that, oh, this patch may change the RV's location, altitude, and flight mode status. We can also realize that this patch may be affected by the terrain environment condition. So we call this identified physical state and environment condition as physical state. Next, we need to find a specific set of input triggering the patch code. But how can you do that? Our main idea is that if we mutated input related to the identified physical set, we are highly likely to trigger the patch code. Indeed, when PatchVerif change on RV's flight mode into the circle flight mode, the PatchVerif successfully trigger the patch code on the below. Next component is analyze the patch type because the PatchVerif bug oracle apply for different bug oracle algorithm according to the classified patch type. However, I'd like to skip this part, but please check our paper if you want to know about detail. And then let's jump into the component 4 and 5. This component is for mutating test cases and then detecting a buggy behavior created by a faulty patch. PatchVerif execute the same test case on 2 different simulators. On the first simulator on the left side, execute unpatched version of the software. On the other hand, the another simulator on the left side, this simulator execute patched version of the software. Our mutation algorithm is quite simple. The PatchVerif assign a value greater or lesser than default value into an input. In here, input denote an environment condition, configuration parameters, and user commands such as ground speed of the vehicle. If the executed input cause any negative impact, such as increased position error or increased battery consumption, in that case, PatchVerif keep increasing or decreasing the input's value. In order to clearly understand this mutation algorithm, let me give you an example. So in this example, PatchVerif already increased this vehicle's ground speed by 5 meters per second. The figure on the below shows before we deploy faulty patch. However, after we deploy faulty patch, the patched version shows increased position error and battery consumption. At this point, PatchVerif noticed this negative impact of the patch code, and then PatchVerif decided to keep increasing this ground speed, such as 10 meters per second. As a result, the patched version shows more increased position error and battery consumption. At this point, PatchVerif concluded, okay, this given patch code snippet is faulty. Why? This is because only patched version shows negative impact compared to unpatched version. Okay, evaluation. In order to evaluate a PatchVerif, we manually correct 1,000 patches created by developers. Next, we verify the correctness of the manually collected 1,000 patches. As a result, PatchVerif discovered more than 100 previously unknown faulty patches. Around half of them have been patched by corresponding developers. Let me explain one case study. In this case study, a faulty patch is for implementing a new circular shape geofence. The simulator on the left side shows before we deploy faulty patch, and simulator on the right side shows after we deploy faulty patch. So as you see, in the case of the unpatched version, the vehicle will avoid the square-shaped object and continue given mission. On the other hand, unfortunately, in case of the patched version, the vehicle is stuck near the circular-shaped object and then failed to complete a given mission due to the buggy behavior created by a faulty patch. Okay, summary of my talk. Creating patches for RV control software is error-prone. Why? This is because understanding patch-introduced behavioral modification is hard. In order to tackle this challenge, we developed a new patch verification framework. Its name is PatchVerif. PatchVerif first extracts an input related to the patch and then generate a new test case by mutating the identified input. As a result, PatchVerif discovered more than 100 previously unknown faulty patches. Okay, this work was supported by DARPA and ONR. We really appreciate their support. This is end of my presentation, and I'm happy to take any question. Thank you.